Right now, we are hearing a lot about the latest release of the DeepSeek model and its impact across various domains, including the stock market. In this video, I want to go over some of the important design elements of the DeepSeek architecture and explore why the authors claim it's manageable and possible to train a language model with moderate computing power. The first challenge in inference with a transformer-based language model is storing the keys and values for generating the next token in an autoregressive manner. To make this prediction fast and efficient, we need to store all the keys and values of the tokens we've processed so far in order to generate the next token. The bottleneck here is that as the sentence gets longer, we need more storage capacity. For a reminder, we compute the keys and values by multiplying the input embedding vector by the respective transformation matrices. To solve this, the authors propose projecting both the keys and values into a lower dimensional space using a down projection matrix for keys and values. Then, when we need to separate the keys and values, we project them back up using two new matrices. This way, we only need to store the compressed version of the keys and values, and we only transfer them back to the original space when we need to compute the attention output. Another design is that if we write the attention formulas for computing scores, we can combine the up-projection matrix of keys with the query matrix transformation and do the same for the up-projection matrix of values with the output matrix transformation. This way, it is not necessary to compute the keys and values separately. The next major design is using a special mixture of experts structure. After calculating the attention heads, we have a feedforward layer that transforms and refines each token embedding independently. In a conventional MOE, we replace the standard feedforward networks with a set of multiple experts, each functioning like an independent feedforward network. Depending on the context and the subject of the input tokens, only a subset of these experts will be activated for each token. This leads to using only a portion of the parameters for each token and reducing computations. In the proposed DeepSeek architecture, the authors observed that by keeping the number of experts low, each expert has to cover a wide range of subjects, which makes it hard for them to focus and specialize in finer topics. To address this, they divide each expert into multiple smaller experts with a reduced hidden dimension. For example, they divide the hidden dimension by a factor of m and increase the number of experts by a factor of m to maintain the same computational cost. This enables better specialization and more efficient knowledge distribution. After training, the authors also observed that many experts are learning some general shared knowledge. As a result, many experts end up learning redundant and similar information. To address this, they introduced shared experts dedicated to capturing common knowledge across different contexts. All tokens are passed through these shared experts to learn this common context. For the remaining tokens, the previous method is used to select the most relevant experts. To maintain the same computational cost, the number of specialized experts is reduced by the number of shared experts. To find gating mechanism G, we first calculate the dot product of the token embedding with each expert centroid vector. These centroid vectors are learnable and represent the context or specialization the experts are focused on. The dot product shows how well the embedding vector aligns with each specialized expert, and we select the co-experts with the highest alignment. Let's consider an example with 3 tokens and their embedding vectors, as well as 4 experts, each with their learned centroids. To find the most appropriate expert, we calculate the dot product of each token's embedding with the centroids of the experts. For example, for the first token, we compute the dot product and apply softmax to get the activation scores. If we want to select only 2 experts, we choose experts 2 and 4. The final output would then be the output from experts 2 and 4 plus the shared expert log with the skip connection. The final design concept I will discuss is multi-token prediction. The idea is that instead of predicting only the next token at each step, the model predicts multiple future tokens sequentially. This helps the training process by providing stronger learning signals for the model. The architecture consists of a main model that predicts the next token, along with multiple multi-token prediction modules, each responsible for predicting additional future tokens. First, the main model predicts the next token. Then, for the first MTP module, we shift the input sequence and pass it through a shared embedding layer to obtain embedding vectors. Additionally, we use the output of the transformer block from the main model as an additional input to the next layer. After applying normalization, we concatenate the transformer output and the token embeddings. This combined representation is then passed through a linear transformation projected back into the embedding vector space. The process continues through multiple MTP modules where each module reuses the previously computed embedding vector as an additional input for the next prediction. Building on this model, the authors introduced the R1 model, which uses reinforcement learning for logical reasoning, and I will discuss it in the next video. Please subscribe and like this video if you find this useful. Thank you and see you later.